Hey everybody. Today we're going to do another example computing volume using the washer method. Before we get started with the specific example, let's quickly recap the process that we're going to use. First, we're going to sketch the region. We're going to include a typical rectangle. Then we're going to imagine it rotating. We're going to imagine both the region rotating and the rectangle rotating. So we're going to picture the solid and the washer that's traced out by that rectangle. We're going to determine the inner and outer radius of a typical washer. Those will typically correspond to the functions that define the region on the top and on the bottom. We're going to write down a formula for a single washer, determine the limits of integration, probably by setting a couple of functions defining the region equal to one another, write an integral representing the volume of the entire solid, and then probably the easiest part will be to actually integrate and simplify to get a numerical answer. So here's the actual problem we're going to do. The area enclosed by y equals the square root of x squared plus 7 and y equals 4 is rotated about the x-axis. Find the volume of the solid generated. So let's start by drawing the region. I've drawn those two curves, y equals the square root of x squared plus 7, y equals 4, and shaded in the region that they are enclosing. I want to imagine this rotating about the x-axis. As I do that, I also want to imagine this rectangle rotating about the x-axis. Can we picture this? The rectangle is going to give us a washer, and the shaded region is going to give us something that is kind of donut shaped, but with a flat outer edge. Let's see a picture of it. There we go. Both the solid of revolution there on the left and a typical washer there on the right. The outer radius for the washer is going to be defined by the top curve, y equals 4, and the inner radius will be defined by the bottom curve, y equals the square root of x squared plus 7. Now, we can get a formula for the volume of that typical washer. Pi times the outer radius squared minus the inner radius squared times the thickness of the washer dx. Overall, pi times 16 minus the quantity x squared plus 7 dx. Before we can set up the integral, we have to figure out where those washers begin and end. We have to find the intersections of y equals 4 and y equals the square root of x squared plus 7. So I'm going to set those two equations equal to each other. Square root of x squared plus 7 equals 4. Square both sides, move the 7 over, and take the square root. X equals plus or minus 3, as the graph would suggest. Now we're ready to get an integral. There's the general formula, so let's take out the a, b, and the r's and plug in what we know they are. A and b, the endpoints of that interval, are going to be -3 and +3, and the difference between the squares of the radii is 16 minus x squared plus 7, as we saw a couple slides ago. A tiny bit of simplification, antiderivative, plug in values, and we're about to get the final answer, 36 pi, about 113.10.